Dr. Laughton again. Today we are going to be talking about how we find angles around intersections that we're missing some value. This is going to be important in a wide range of fields, from mechanical engineering to electrical engineering, but for me in civil environmental engineering, we actually apply this all the time in transportation design, looking at roadway intersections. So let's do a little review and then we'll apply it in a problem. Bit of vocab to remember from geometry. When I say that two lines are parallel, they are going in the same direction, they are never going to intersect. We indicate that generally by having a little arrow. Sometimes you'll see a hatch mark that indicates these paired lines are parallel. When we talk about perpendicular lines, this is sort of our T intersection in transportation engineering. They intersect at two right angles. Now, when I look at two intersecting lines that are not necessarily perpendicular, maybe they are, maybe they're not, who knows? I have four angles that are formed around this intersection. We'll call them A, B, C, and D. Now, going from one edge of a line to the other, like such, this ends up being 180 degrees. So I could write that A plus B, whatever those two angles are, must be 180 degrees. Likewise, the other side of the line, C and D, must add up to 180 degrees. Now if I have two 180s, that means when I go all the way around the entire intersection and return back to where I started, I've covered 360 degrees. This means that A plus B plus C plus D must equal 360. Now, one more nice thing about this scenario is that when I have two intersecting lines, presuming both lines are completely straight, the opposite angles are the same. So I can also say that A is the same as angle C and B is the same as angle D. When they're opposites, they will be the same. Now let's move up and think about what happens when I have two parallel lines with one line intersecting both. In this case, I have formed 8 different angles around my scenario. I'll once again label them. We have A, B, C, and D, as well as E, F, G, and H. Almost forgot the vocabulary there for a minute. Now, all of the ideas that we came up with down here are going to be the same. A plus B is still going to be 180. C plus D still also has to be 180. If I go all the way around A, B, C, and D, that's 360. Same thing applies. E plus F, 180. E plus H, 180. All the way around E through H, 360. Also, our opposites are still going to be the same. So I can say that A is still equal to C and B is still equal to D. But something interesting happens when we have two parallel lines. If I was to cut this out and slide it up, keeping this diagonal line in alignment, it's going to look exactly the same around this intersection. Kind of handy. So that means where E is would perfectly align with where A is. So A not only equals C, it also equals E and G. So the same thing with this diagonal. B and D also equal F and H. That means I could actually start adding up angles that are around different parts of the parallel line. So we said that if A plus D is 180, I could sub in E. So something like E plus D is still equal to 180 degrees. G plus B, G plus D, still all 180. Kind of handy when we're thinking about roadway design. Generally, we have intersections that go all the way around, so all of our angles have to sum up to 360 degrees. And in a lot of cases, our roadways are going straight through an intersection, so I can assume that the straight line adds up to 180. Now, our example that we're going to do today is actually using something from our campus. So as you can see, around Bond Hall, the administrative building on campus, we have 4 streets that intersect. We have Jones that runs through 2 intersections. We have Moultrie going across the front of the building. Also connecting with Jones, we have Richardson. And on the far side, we have Haygood. At the intersection between Moultrie and Jones, we know one of the 3 angles that's formed around that intersection. We know that on the outside, this is a 90-degree angle. Over at Haygood and Moultrie, we once again have another 90-degree angle. And over at the intersection of Richardson and Jones, when we look at the angle all the way around the outside of the intersection, we're told that this is 280 degrees. What we are trying to find, we have a couple of interior angles that we need to find. We need to know what is the unknown angle between Jones and Moultrie, between Richardson and Haygood, and then between Richardson and Jones. So the thing to remember here, whenever we are going all the way in a full circle around an intersection, that's going to have to add up to 360 degrees. Or if I am going from edge to edge on a straight line, that will add up to 180 degrees. So we can actually go ahead and start identifying a couple, 2, of our intersections. Up in the top, we have Jones and Moultrie intersecting, and since Jones is a straight line, the unknown angle is going to be a 180 straight line minus the 90 that we have that we already know. So this intersection is also a 90-degree angle. Indicate that with a right angle. Down with Jones and Richardson, we go all the way around the intersection, so a full 360 degrees, but I already know 280 degrees of that distance around. So doing a wee bit of math, this ends up being an 80-degree angle. So now we have 2 of our unknown angles inside of this 4-sided figure, a quadrilateral, but we need to know this 4th one. Now, a little trick, kind of like when I go all the way around a full intersection, if I do some rearranging and sliding, you could justify it to yourself, but the trick is the interior sides of a four-sided figure are all going to add up to 360 degrees. Feels like we have a magic number in there, 360, something good to remember. So, if I am trying to find this angle, just for space, I'm going to draw it over here. We have the total that we expect to see, 360, all the way around, minus the three angles we already know. So I have two that are 90 degrees, and one that is 80. I can plug that through my calculator, and it ends up that this unknown angle is 100 degrees. So, pretty straightforward application of finding angles, when we know some of them, around intersecting lines. Now, we could also think about using those angles to justify if streets are parallel or perpendicular. Remember, perpendicular, they have a 90-degree intersection around them. So the Moultrie and Jones, in this case, are perpendicular. We could also identify if streets are parallel, meaning that they would have constant angles on both sides of them. So in this case, Jones, Haygood, not quite parallel, because we've got 90s up at the top, but we've got 80 and 100 down on the bottom. So there is some variation. All right, good luck on your homework problem.